Welcome to the sixth lecture of this week. In the last lecture, we saw how we can analyze a laminate using Reed's method. We will do one particular case related to that today. So, we have chosen a cross ply laminate which is symmetric and that is clamped at the 4 edges. So, it is not always possible to get a Levy's solution or Navier solution for all the laminates. For example, if we have this kind of laminate which is clamped at 4 edges, then we cannot use those sign functions in our approximation. So, because that will violate these boundary conditions, or there are some cases, for example, if it is laminated composite plate, then suppose it is a symmetric angle ply laminate, but simply supported, but even then also we cannot the governing differential equation is not such that a sin function will let you separate out terms or sin cosine functions, or even sometimes the boundary condition also does not let us do that. In that case, we need a more robust approach. So, with Reed's method we can pretty much solve all types of problems. So, here we have a symmetric cross ply laminate that is under a transverse load, and let us say the load is Q. Now, here we know that because it is symmetric, we can use this equation separately. We do not need the in plane equations, and then after putting the definitions of mx, my and ms in terms of the derivatives of w, we get this, and we have a minus sign here because by definition mx, my, ms have a minus. So, finally, this quantity this is negative here. Now, we need to make the assumptions. So, let us assume, and we know that the assumption should be such that it satisfies our essential boundary condition. In our case, the essential boundary condition is homogeneous. So, let us assume terms like this: n equal to 1 to n, m equal to 1 to m. Capital X is a function of x and small y is a function of y. So, we will choose a function of x and there are total m like that, and similarly choose a function of y and there are total n like that, and then we multiply them and we make their combinations and we get total mn number of combinations, and their sum is weighted by these unknown constants w m n, which is to be evaluated, and that gives us w. So, previously when we were discussing in general the Reed's method, we wrote w x y as a sum of a w j multiplied by phi w j, where j can go from 1 to let us say p, because we have already n here. So, let us use a different notation p. So, this is actually this, but written in a different form, because we are writing these w j's as combination of these x's and y's. So, here p is equal to m n. So, instead of one index here, we have to deal with double index. So, after we represent them by this with this separation of variable, now let us also this is x m and this is x n. So, there are total capital M number of these x's and capital N number of these y's. So, x m as a function of x, let us write this as x a to the power m plus 1 multiplied by 1 minus x by a whole square, and similarly y n, which is a function of y, let us write this as y by b to the power n plus 1 multiplied by 1 minus y by b to the power square. Now, the essential boundary conditions here are, this is clamped. So, we know that the essential boundary condition is w is equal to del w by del x equal to 0 at x equal to 0 and at x equal to a, and w is equal to del w by del y is equal to 0 at y is equal to 0 and y is equal to b. So, this has a dimension a along x and this has a dimension b along y. Now, these approximations satisfy these conditions and this is enough for us. Now, what we will do is we will put these approximations in the weak form. So, we have m x here and m x is written as this, and then we have del 2 w by del x 2, and del 2 w by del x 2 is nothing but this. So, del 2 w by del x 2 is again summation n is equal to 1 to n, m is equal to 1 to m. So, this is del because w is a function of both x and y. So, this is del, and then we differentiate this x 2 x m y n. Now, here this is a function of only x and this is a function of only y. So, if I differentiate that, all we get is just second order derivative of this with respect to x. So, we write n is equal to 1 to n, m is equal to 1 to m, then we have d 2 x m by d x 2 multiplied by y n. Now, because x is function of only small x, so we are writing it is as d not as del, and then w m n remains as it is. Similarly, we have del 2 w by del y 2, and this we can write as n is equal to 1 to n, m is equal to 1 to m, and we can write this as del 2 w second order derivative with respect to y of x m y n, and then w m n is not a function of either x or y. So, this we can write as this x m, and then we have d 2 y n dy 2, and then we have w m n, and then similarly del 2 w del x del y can be written as small n is equal to 1 to n and m is equal to 1 to m, and then we can write this as dx m by dx dy n by dy and w m n. Similarly, if I take their variations, just the because this x m y n they are all defined functions, we cannot vary them, but we can vary w m n's, and that is what we have done here. Now, here when you are writing the when I am writing for this, we are using the indices I and j, and here we are indices m and n. Now, it does not matter, we could have used the same indices also, but here we are using different indices just to show that they are coming from, I mean they signify different quantities. So, this is the variation of w's and their derivatives, and this is the moment terms. Now, after that similarly here also we have replaced, we had w here and we have replaced this by w del w by this. Now, after doing that, our next step is we have to separate out this delta w m n's. So, I have to write it in such a way that it can be represented as delta w 1 multiplied by something plus delta w 1 multiplied by something, and so on up to the last term delta w capital M capital N multiplied by something, and that is what we have done here. So, we have just expanded this summation, these summations, and and separated out delta w 1 delta w 1 all the way up to delta w capital M capital N. That means, all the components of delta w m n, and the same thing has been rewritten as this. So, delta w 1 multiplied by this entire quantity delta W all the way up to delta W small n multiplied by this quantity, and it goes on then all the way up to delta W capital M capital N multiplied by this quantity. Now, we can notice here that when I have, if I expand this sum and then if I just multiply the first term of it, which is delta W x 1 by del x 2 dW x 1 by del x 2 multiplied by y 1 into variation of W 1 1, then that quantity just gets multiplied with this quantity. So, this summation remains as it is. Only thing is that depending on the term here, we have some d2 x m by dx 2 into y n and delta of W m n, and as m n changes these indices changes, but whatever is here that remains as it is. So, this gives me an expanded form, and so we have delta W's and their coefficients. Now, again these delta W's are arbitrary. So, delta W 1 1, delta W 1 2 all the way up to delta W capital N, they are all independent and arbitrary variations, but our requirement is that the sum should always be 0, and that is only possible when whatever I am multiplying with delta W 1 1 is individually 0. That means, the terms inside the whatever I have written inside the square bracket is independently 0. Similarly, for all the terms, so here also whatever I am multiplying with delta W m n, so everything inside the square bracket is separately 0. So, this gives me total capital M capital M multiplied by capital N number of equations, where the mnth equation can be written as this. So, this signifies a set of linear simultaneous algebraic equations total. There are total m into n equations, and there are total m into n unknowns, because our unknowns are W m n and they are total m into n in number. So, if we solve these equations, we can uniquely find out W m n, and once we get W m n, we can substitute back to its original approximation, and that gives me the solution for W. So, from here with m going from 1 to m and n going from 1 to n. So, find out W m n from here, and then use in the solution W x y, which is n is equal to 1 to n, m is equal to 1 to m, x m which is a function of x, y n which is a function of y, and here we have W m n. So, this completes this solution, and again because this laminate was symmetric, we could separately solve the third equation, that means the out of plane equation. If the laminate was not symmetric, we would have to solve all the three equations. In that case, we would get more number of equations and we have to solve them simultaneously. Now, so what we have seen in this week is when we solve these differential equations, our goal is to write the solution as a series, and then finally we get a set of algebraic equations in terms of the unknowns in the series, and these algebraic equations are linear equations which we can solve and find out those unknown terms, and then by putting it back in the approximation, in the series form, we can get the solution. Now, in the Navier solution, in the Levis solution, we solve the differential equation as it is, but in when we do a Reed's method based solution, then we do not directly solve the differential equation, rather we bring into a form like this, a variational form, and this is also called a weak form, these forms are called weak form. So, whatever we derived in the last lecture, all those are called weak forms, and then we, by putting it in the weak form, then satisfying the weak form, we get the again a desired set of linear algebraic simultaneous equations. Now, instead of writing it in the form of virtual work equation, we could have written the total potential energy also of the laminate, and we could have minimized that, and that also would give us similar solution. So, with this I would like to finish this lecture here. Thank you very much.